Greetings and welcome to another week of our geometry recordings. We are in week 7 this week, and we're going to start just like we do every week with a warm-up question that I do want to see you complete in your math notebook. When you turn in your weekly notes, I should see notes from this recording and labeled as such. Please make sure when you're turning in your notes, you're doing a good job of labeling them. That's for you to ensure you get full points. Label it with Unit 6, Session 5, and then include your notes from Session 5. And then when you move on to Session 6, there should be a label that says Unit 6, Session 6, and then the notes will come after that heading for Session 6. There should also be a heading that says weekly recording, week 7, and the notes from your recording should come after that. So I do want you to make sure that you're organizing your notes better. Use headings, like I said, from each session and put your notes under that session. If you're not doing that, there's a good chance that I'm not able to see that you took notes from every session, and you might be losing points because of that. So make sure you're using proper headings in your notes. And again, there should be a heading for the weekly notes. So when you head the notes for this week, the recording should say Week 7 Recording Notes. And again, right under that, I should see your response to this warm-up question. So what is the warm-up question? We've got a coin. We're going to toss a coin, and we also have a 6-sided dice that we're going to roll. I want you to find the probability of landing on the head side of the coin, as well as rolling a 3 on the dice. So first, decide if this is an independent or dependent event, because that will help you determine how you're going to find then the probability of landing, throwing a coin, landing on heads, and rolling a 3 on a dice. So go ahead and click pause, work on this in your math notebook, and then when you're ready to check your work with mine, go ahead and click play. All right, so is this an independent or dependent event? Do these two events affect one another? Does tossing the coin affect the number that we would get on the dice? No, these two events are independent of each other. One outcome does not affect the outcome of the other event, so it's an independent event. So we are trying to find, let's use our fancy probability notation. We're trying to find the probability of landing on heads and getting a 3 when we roll our dice. So when we find the probability of independent events, we find the probability of each event occurring on its own, and then we multiply those probabilities together. So we're going to find the probability of throwing a coin up and landing on heads, and then we're going to find the probability of rolling a dice, 6-sided dice, and it landing on 3. So what is the probability of a coin landing on heads? We'll do the probabilities below. It'd be 1 out of 2. There's one head out of heads and tails, so it's 1 out of 2. And then a 6-sided dice, there's only 1 3, so the chances of it landing on 3, 1 out of, it's a 6-sided dice, so 1 out of 6. We multiply those two probabilities together, and I get 1 over 12. So that is the probability of these two events occurring, 1 out of 12 of landing on a head and rolling a dice and getting a 3. All right, so that's some good warm up of what we did last week of looking at independent and dependent events. So what are we doing this week? This week we are going to start with Session 3, which is looking at two-way tables and finding the probability of different events based on the data in those two-way tables. Then we're going to move on to Session 4 and learn what a compound event is and how to find probability of compound events. And then we're going to get started on a project where you are going to a fair and going to find the probability of some different games at the event. So we're just going to get started on that project this week, and then if you need more time next week to work on it, that is okay. The due date will be for the Unit 6 project will actually be in next week's assignments, in the week 8 assignments. So again, just getting started on this. You might finish it this week. If you need more time, you can work on the Unit 6 project into next week as well. So let's take a look at two-way tables. All right, so in session 3, you're going on to look at two-way tables. Two-way tables. So we can use two-way tables to deal with two different variables. And whenever we're talking about two variables, we can refer to that as bivariate data. Bi, you get that prefix bi meaning two. So two types of variables that we are referring to. And we can use two-way tables to examine the relationships between two variables. And we can use that table then to analyze survey data. So here's an example down below of a two-way table. We are comparing two sets of variables or bivariate data. So if we were to ask a group of people and divide that group of people into males and females, those would be our two categories, whether they would prefer to have an SUV over a sports car, and then for each category of males and females, record the answers. So if we were to look at this two-way table, we could see that 5 males preferred a SUV and 7 preferred a sports car, where with females, 9 would prefer to have a SUV and 4 would prefer to have a sports car. So if we were looking at this table, could you answer this question? If you could have a new vehicle, oh, that's what the question asked, sorry. So what I was going to ask is, can you determine the total number of people surveyed? Can we determine the total number of people surveyed from looking at this this table? Well, sure. Let's first find all the totals. We can find the total number of people who'd want an SUV. 5 plus 9 is 14. And then the total number that would want a sports car would be 11. Add those up and we get 25. So there's a total of 25 people. We could have added our rows up too and gotten 12 for males and 13 for females, which adds up to a total of 25. So either way we do it, whether we're adding the columns up together and then that total, or the rows and that total, we come to the grand total of 25 people who were surveyed. I'm going to go on to the next slide where we're going to look at this table a little bit more in depth and talk about different types of frequencies we can look at. So when we give in two-way tables, one thing that we can calculate is the joint relative frequencies. And the joint relative frequencies are the values in each category divided by the total number of values. So remember, the total number of values we just found is 25. Whoops, no, actually not. Ignore that. Ignore that for a second. It was 25. I was correct with saying that. I thought for some reason it wasn't a total of 25, but we did. On the previous slide, we found the total number of values to be 25, right? So that means the total number of people that were surveyed, we found that there's 25 people surveyed on the previous slide when we added all our numbers here. So the total number of values is used to find the joint relative frequency. So let's go ahead and find the joint relative frequency in this table that we've been looking at. So the joint relative frequencies are going to be the values in each category. So 5, 9, 7, 4, those are the values in each category. And we're going to divide the value in each category by the total number of values. And in this case, it was 25. The survey was asked of 25 people. So if we take 5 and divide it by 25, what do we get? We want to write joint relative frequencies as a decimal. So 5 divided by 25, we get 0.2. So there's one of our first joint relative frequencies, going to be 0.2. That might be a little hard to see in orange. Let's change to blue. So it'd be 0.2. Then to find the joint relative frequency of females choosing an SUV, we're going to take 9 and divide it by 25. I'm going to grab my calculator, type in 9 divided by 25 to find that decimal, and I get 0.36. I'm going to continue this pattern. The joint relative frequency of males choosing a sports car would be 7 out of 25. Do the division there, and we get 0.28. And the last one, 4 divided by 25, which represents females choosing a sports car. 4 divided by 25 is 0.16. So these are, since I changed color, we're going to change this, blue. These are our joint relative frequencies in blue. All those numbers in blue. Now, the marginal relative frequencies, we find those, let's do that in purple, the marginal relative frequencies is another way that we can look at our table and analyze it. And we find these by adding all of our joint frequencies together in each column and row. So if we were to find the marginal relative frequency of SUVs, we're going to add 0.2 plus 0.36. We add the joint relative frequencies in each column and row. So if we're to find for SUVs, we add 0.2 plus 0.36 and we get a total of 0.56 or 56%. Again, writing that as a decimal and writing it in purple. For a sports car, we would add 0.28 plus 0.16 and I get 0.44. And now I'm going to do the totals for my rows. So the marginal relative frequency of males is 0.2 plus 0.28. We get 0.48. And do the same thing for the marginal relative frequency for females, adding 0.36 plus 0.16, and we get 0.52. Now, a pattern that will always occur when you add your marginal relative frequency totals together. So when I add this column together and this row in the column, my total here should always add up to 1. It should always add up to 1. So when I add this total, my row, or I'm sorry, my row, if I'm doing my row, 0.56 plus 0.44, what do I get? I get 1. When I add the row totals together, 0.48 plus 0.52, I get a total of 1. If you do not get a total of 1 over here in this corner, you have done something wrong. You've done some math wrong. The total should always be 1. When we add up all of our marginal relative frequencies, when we add up the rows and the column, we should always get 1. So remember that, and that will help you to see if you've made any mistakes. And then we can use the data that we've just calculated to answer these two questions below. So it says, if a person is a male, what is the probability that they will choose a SUV? So if they are a male, so we're only dealing with this row here because it asks if the person is a male. So we're only looking at the male row. What is the probability that they will choose a SUV? Right here, it would be 0.2. We have a 0.2% or a 20%. So 0.2 or 20%. If we're looking at percentages, if we have these in percentages, they would always have to add up to 100%. Just throw that in there. And then the last question I want us to answer before we stop this recording, if a person chooses a sports car, what is a probability that they are female? So now we're only looking at the sports car column. Sports car column. If a person chooses a sports car, what is the probability that they are female? Well, it's right here, 0.16 or 16%. So that's how we use two-way tables. Is a lot of times you'll be answering questions about the two-way tables, and it'll be based on a certain row or column. Just like we did with these examples. So I'm going to go on to the next slide. So event is an event made up of two or more simple events. And we've got two types of compound events that we're going to focus on in session 4. That is mutually exclusive events and mutually inclusive events. So mutually exclusive and mutually inclusive events. So you might be wondering, what do those terms mean? Let's start with mutually exclusive events. So mutually exclusive events are events that cannot occur at the same time. They cannot occur at the same time. What does that mean? What are some examples of things that cannot occur at the same time? So let's say we've got another coin. If we were to toss that coin and tossing a coin and getting heads and tails on that same toss is mutually exclusive. We can't get both heads and tails. We can get one or the other, but we can't toss a coin and get heads and tails from the same toss. That's impossible. They cannot occur at the same time. So tossing a heads and tossing tails are mutually exclusive events. They cannot happen on the same toss of a coin. Another example of mutually exclusive or events that cannot occur at the same time would be turning right and turning left at the same time. You can't do that. Either we turn right or we turn left. We can't turn two different directions at the same time. So mutually exclusive cannot occur at the same time. So how do we find the probability of mutually exclusive events? Here we go. Here's our little formula down here. So again, we're going back to event A and B. So if we've got event A and event B, and they are mutually exclusive events, meaning these two events cannot occur at the same time, then to find the probability of either event happening, so the probability of event A or B occurring, we find that by finding the probability of our first event, event A, and adding it. So remember when we were finding independent events probability, we were multiplying the events together. Now we're adding, and then we would add to it the probability of the second event. So again, make sure we understand the notation here. Event A or B, we're trying to find the event of either of those events occurring. When we see or, we should note in our head that we're adding the events together, or adding. Are you ready for an example? Oh, not quite yet, not an example. Before we do that, we're going to look at mutually inclusive events. So inclusive events are the opposite of exclusive events. They are events that can occur at the same time. They can occur at the same time. So what are some examples? Turning left and scratching your head. You can scratch your head. You can reach up right now. You can scratch your head and you can turn left. You can do those things at the same time. Rolling a 6 and then rolling an even on a number cube. Those are inclusive events because they can occur at the same time because 6 is in fact an even number. So those two events, because they can occur at the same time, are considered inclusive events. So because inclusive events can happen at the same time, you don't want to double count the probability of where the events overlap. So what we're looking at doing is getting rid of where the events overlap. We're going to subtract that out when we find the probability of inclusive events. So here is our formula. Write this down in your math notebook. So when we've got inclusive events where there is overlapping, and we want to find the probability of an inclusive events A and B, A or B occurring, I should say, A or B, the probability of event A or B. What we do is we go about the same way we did with exclusive events where we're adding the probabilities together, but now look what we're adding on. We're going to subtract out where the events overlap. And that would be written as the probability of event A and B. See right here? That means the probability that both A and B can occur at the same time. So again, you can think of it as where they overlap. So make sure you are writing down what this notation means. When you have a capital P in parentheses A and B, that means the probability that both A and B occur at the same time. It's where that overlap occurs, and we want to subtract that out of the probability. So let's go on to the next slide where we're going to look at some examples now. We're going to first identify whether an event is mutually exclusive or inclusive. And then we are going to find the probabilities using the correct formula, if you will. So the first question, it says find the probability of rolling a 5 or an odd number on a 6-sided dice. Can these events occur at the same time? Can you roll a 5 and an odd number at the same time? You can, because 5 is an odd number. So since these can occur at the same time, this is an example of an inclusive event. All right, so now let's actually find the probability of rolling a 5 or an odd number on a 6-sided dice. So remember, when we are finding the probability of mutually inclusive events, we take the probability of our first event, we add to it the probability of our second event, and then we subtract out the probability of both occurring, that overlapping probability. So now let's apply it to this specific question. So we're going to find the probability of rolling a 5. We're going to add to it the probability of rolling an odd number. And then we're going to subtract out the probability of rolling a 5 and an odd number. So again, this is to find the probability of, I guess I should have over here said 5 or an odd. Run a little bit, squeeze that in there, 5 or an odd. That is originally what we were trying to find. So now let's go ahead and write in the actual probabilities of each of these broken down probabilities. So what is the probability of choosing or rolling a 5? Well, there's 1 5 on a 6-sided dice where there's 6 different outcomes, 6 different numbers it can land on. So there's only 1 5, so you got a 1 out of 6 chance that it's going to land on a 5. What are the chances it's going to land on an odd number? Well, we know that there's 3 different odd numbers. Those numbers would be 1, 3, and 5. So a total of 3 odd numbers that we can land on out of, again, a total of 6 different numbers that we can land on. Now, this is where it gets a little funky, where we want to find the probability of 5 and an odd number. So this is our overlap. So 5 really dictates the probability here. There's only 1 5. It is an odd number as well, but there's only 1 5 that would be 5, one number that is 5 and an odd. That's the number 5. So we only have a 1 out of 6 chance that it's going to be a 5 and an odd number when we roll the dice. So now we're ready to add up all of our probabilities, and we can see that that 1 6 minus and 1 6 will cancel out. We're left with 3 6, 3 over 6, which we can reduce to 1/2. So that is our final answer, 1/2 probability of rolling a 5 or an odd number. So there is a 1/2 chance that we would roll a 5 or an odd number if we were to throw a 6-sided dice. Looking at the second problem, it says find the probability of rolling at least 1 4 when rolling 2 dice. So is this mutually exclusive, where they cannot occur at the same time, or inclusive, where this can occur at the same time? So let's look at that question again and decide. Find the probability of rolling at least 1 4 when rolling 2 dice. So essentially, we're looking at what is the probability of rolling a 4 or a 4. Rolling the dice 1 time and then rolling the dice a 2nd time and getting at least 1 4. So can those events occur at the same time? Yes, because if we're rolling 2 dice, there's a chance that both of those dice, we can roll a 4 on both of those dice at the same time because we've got 2 different dice. So this is another example of inclusive. They can occur at the same time. They can occur at the same time. So this is an example of mutually inclusive. And now we are going to find the probability. If you want to try to click pause and solve this on your own and then check your work with mine, you're more than welcome to do that. I'm about to solve this though, so if you want to try it on your own, go ahead and click pause now. So let's go ahead and write out kind of our blueprint here that we're finding the probability of 4 or 4. And to do that, we're going to find the probability of 4 on our first, add to it the probability of 4, happening again, rolling a 4, and then we're going to subtract out the probability of rolling a 4 and a 4. Are you ready? I'm ready. So what's the probability of rolling a 4? Well, there's 1 4 on a 6-sided dice, so 1 out of 6. So again, the probability of 4, again, is going to be 1 out of 6. This is where we subtract out the overlap now of rolling a 4 and a 4. So I mentioned a little bit ago that when you see or, when you're trying to find the probability and it says or, you're going to be adding together, or should let us know that we're adding the probabilities, where and means we're going to multiply the probabilities. So if we want to find the probability, let's kind of change font up here, of getting a 4 and a 4, we're gonna take the probabilities and multiply them because we see that word and. So we know the probability of 4 is 1 over 6, and then we're going to multiply it times the probability of another 4. Landing on 4, which is 1 out of 6. Multiply those together and I get 1 out of 36. So kind of going back to what we learned last week, when we see that keyword and we're finding the probability of 2 events and it says and, find the probability of this and that, we multiply those probabilities. So 1 6 times 1 6, we get 1 over 36. So let's go ahead and add that back into our calculations down here. 1 over 36 is going to represent the probability of rolling 4 and a 4. So now we can do the math. But we know, looking at our fractions, that in order to add and subtract fractions, we have to have the same denominator, right? We don't right now. We've got a denominator of 6, 6, and 36. So we need to find a common denominator. And I'm looking, it's pretty obvious that that's 36, right? So if I multiply this fraction, the top and bottom, times 6, I get 6 out of 36, which reduces to 1 6, but now we have that common denominator. 6 over 36, and then subtract out that 1 over 36. So we're adding now our fractions with the same denominator. So really, our denominator is going to stay the same, and we can focus on our numerator. 6 plus 6 is 12, minus 1 is 11. So that is our final probability, 11 out of 36 chance of rolling a 4 or 4. So in both these examples, we looked at mutually exclusive events. I think it's about time that we look at another example of another type, right? So let's look at one more example and then we're going to stop. One more example. So I'm going to move on to the next slide. So if you want to click pause, go ahead and do that now so you can take notes. All right, one more example. Jump ropes are given out in a gym class. A student has a 1/6 chance of getting a red jump rope. So a 1/6 chance of getting a red jump rope and a 1/3 chance of getting a green jump rope when the jump ropes are handed out. Meg is in this gym class and she is given a jump rope. What is the probability that Meg gets a red or green jump rope? So first, let's decide what type of event are we looking at. Can these events occur at the same time? She's given 1 jump rope. So can she get a red and green at the same time? No. So because these events cannot occur at the same time, we're looking at a mutually exclusive event. The events cannot occur at the same time. And now let's go ahead and find the probability. And again, if you want to try this on your own first, if you think like you want to give this a try on your own, go ahead and click pause, and then when you're ready to check your work with mine, go ahead and click play. So we are trying to find the probability of Meg getting a red or green jump rope. So in order to find that probability, first we're going to find the probability that she's given a red one. We're going to add to it. We see that keyword or lets us know we're adding. And then the probability of getting a green one. And then that's it, because we don't have to subtract out the overlap here. We don't have to subtract out the overlap since we're dealing with mutually exclusive. So the probability of red, 1/6. The probability of a green, 1/3. Again, in order to add these together, we have to have a common denominator. So I'm going to make 6 my common denominator and multiply both our numerator and our denominator by 2 to get 2, 6, so that we have a common denominator. I just changed that 1/3 into 2, 6. Add those together, I get 1 plus 2 is 3, 3 out of 6. That's our probability, which we know we can reduce to 1/2. So there's a 1/2 chance that she's going to get a red or green. That was our last example. So now it's time to move on and answer the key phrase assignment. So we are, all right, ready for the week 7 key phrase assignment that I just put up. So we talked in this session about mutually exclusive and mutually inclusive events and how we can determine the difference between the two. So what you need to do for this key phrase assignment is determine if rolling a dice and getting a 5 or an even number is an example of a mutually exclusive or mutually inclusive event. And then as well, you need to tell me, how do you know? Why did you choose your response? And that's it. So if you have any questions or need any help this week, let me know. Otherwise, have a fantastic rest of your week. In week 7,